Hey everybody, in this video we're going to talk about cylindrical and spherical coordinate systems. So we'll begin by reviewing what we know about the familiar 2D Cartesian or rectangular coordinates. That is, we've got two perpendicular axes, an x-axis and a y-axis, and every point in space can be described by giving an x-coordinate and a y-coordinate. Well, there's another way to describe points in the plane in two dimensions, and that's polar coordinates. So instead of specifying an x and a y, we can specify an r, which is the distance from the origin, and a theta, which is the counterclockwise angle from the positive x-axis. And so with theta ranging from 0 to 2 pi, we can describe every point in the plane with just this pair of numbers. So it's an alternative to the Cartesian or the rectangular coordinates with x components and y components. Why are polar coordinates handy? Well, sometimes different regions, different objects are easier to describe in one coordinate system than another. And so, for instance, take the circle of radius 2. In Cartesian coordinates, we can describe it in terms of x components and y components. But in polar coordinates, that description is really, really simple. It's just all the points with our coordinate 2. Well, what about having the coordinates of a point in one coordinate system and transforming that to figure out what the coordinates would be in a different system? So what if we knew the polar coordinates for a point and wanted to know what the rectangular coordinates would be for the same point? Can we figure out what those coordinates are? We certainly can. And just from what we know about basic trigonometry, that's relatively straightforward to work out. What about going the other way? What if we knew the Cartesian coordinates, the rectangular coordinates of some point, and wanted to figure out what its polar coordinates would be instead? We can do that as well. Okay, so that's polar coordinates. Well, the first thing then we want to talk about are cylindrical coordinates. And cylindrical coordinates are just polar coordinates sort of broken into 3 dimensions. So we take the polar coordinates for some point, and we can then just add a z component to describe where that thing is in 3-dimensional space. So cylindrical coordinates r, theta, and z. The r and theta are just like in polar coordinates. And then, excuse me, the z just gives us the height. And again, theta can range anywhere from 0 to 2 pi, and this can describe every point. With these 3 numbers, we can describe every point in 3-dimensional space. Spherical coordinates are a little bit different. Spherical coordinates, we still have that azimuthal angle theta, which is the counterclockwise direction from the positive x-axis. But then we talk about, instead of dealing with a z, we talk about the distance rho from the origin. So from any point in space, we can talk about its distance from the origin, that distance we call rho. And then we have the polar angle phi, which is measured from the z-axis. Sort of tells us the inclination. And so again, see that we can describe every point in 3 dimensions this way as well, with a rho, theta, and phi. Be a little bit careful when you're looking at different sources. There's not a one universal convention in terms of which angle we call theta and which one we call phi. Different sources use different ways. We're going to do it this way, though, with the azimuthal angle off the x-axis being theta, and phi being the angle from the z-axis. And again, we can let theta range from 0 to 2 pi. What about phi? Well, it turns out that phi can, ranging from 0 to pi is sufficient. Okay, and again, spherical coordinates, why would we bother with them? Some things are much easier to describe in spherical coordinates. Some surfaces we'll work with. One basic example is, again, a sphere in 3 dimensions. In rectangular coordinates, we can describe it, but in spherical coordinates, it's very, very simple to describe. And also, there's the added benefit, if we have some vector that we are describing with spherical coordinates, well, then the magnitude of that vector is just the rho component, as long as that vector is based at the origin of the point that it points to. And then what I'd like to leave you with is seeing if we can figure out how to convert between different coordinate systems. So if you know the rectangular coordinates, can you figure out the cylindrical coordinates and vice versa? If you've got rectangular coordinates, can you figure out the spherical coordinates and vice versa? And if you've got cylindrical, can you figure out spherical, and so on. So think about these, and we'll talk about this in class.